So in our last video, we defined what a congruence class was, and how do we define what objects are inside of a congruence class. So for example, the congruence class of A, mod n, we can think of this in two different ways. The first way we can think of it as it contains all the elements of B such that B is an integer, and B is congruent to A mod n. Now another way to think about this is it's a set made up of all the b's such that if we applied the division algorithm on b and divided by n, it had a remainder of a. So now we're going to look at a third way of describing the elements inside of a congruence class. So this is using coset notation. Now we will formally define what a coset is in the next coming weeks when we start getting into groups. But for now, what we can do is we can think of a coset is a subset of a larger set, and how we create that subset is we take a single element and we multiply that single element by every element inside of the larger set, and this generates a subset for us. So let n be a natural number and a be an element in Z. So first we'll define a coset, or define the coset we'll be working with. So we're going to take the set of integers that is our larger set, and every integer I'm going to multiply it by n. So this set is going to be made up of all n times k, where k are elements inside of Z. So let's take a quick look at this. So as an example, we'll take n is equal to 4. So this gives us 4z. So what is 4z? Well, this is the set of all 4 times k, where k is an element inside of z. So what exactly does this look like? Well, let's start with the element 0 inside of z. If I take 0 and multiply it by 4, what am I going to get? Well, I'm still going to get 0. When I take 1 inside of z and multiply it by 4, 1 times 4 is going to give me 4. 2 inside of z multiplied it by 4 is going to get me 8. Hopefully you get the idea from here. So 3 times 4 is going to get me 12. 4 times 4, 16, and so on and so forth. And since, of course, the integers go up to positive infinity, I have positive infinity times 4 is still going to be positive infinity. Now, of course, this also works in the opposite direction when I'm using the negatives. So negative 1 times 4 is going to give me a negative 4. Negative 2 times 4 is going to give me a negative 8, and so on and so forth. Negative 12, negative 16, and all the way up to negative infinity. So it's not the integers in itself, it's a subset of integers such that every 2 consecutive integers has a distance of 4 units away. So how do we use this in terms of developing the congruence classes? Well, all we're going to do is we're going to take this as a base set here and just add the element A to each one of these. So for example, and actually I'll just go back to the slide so we see it here for a second. So all we're doing is when I take that element A, that representative of the set, I'm just going to take A plus this coset, this new subset of the larger set, where again each unit is n distance away, or every 2 consecutive units are n distances away. So the easy one is 0. So the congruence class of 0 mod 4, what is this in coset notation? This is just 0 plus 4z, or just 4z, which of course is exactly what I have above. Now if I try doing 1, so all I'm doing is taking 1 to every element in this subset of 4z. So what is this going to look like? Well, if I start with exactly how I have it above here, starting at 0, well, I'm going to add 1 to that. 4 is going to become 5, 8 is going to become 9, 12 is going to become 13, 17, and again, all the way up to positive infinity. Working in the opposite direction, again, I'm adding 1, remember, so this is going negative 4 to negative 3, negative 7, negative 11, negative 15, so on and so forth. Let's do one more. Let's say 4, the congruence class of 4 mod 4. In coset notation, this would be 4 plus 4z. And what would this look like? Well, the set would look like kind of what we have above here, except again, I'm adding 4 to each element. So 0 plus 4 is 4, 4 plus 4 is 8, then I have 12, 16, 20, all the way up to positive infinity. And working from the reverse, negative 4 plus 4 is going to give me a 0. Negative 4 and 8 is going to give me negative 4, negative 8, negative 12, all the way down to negative infinity. Now, one thing to note, these two sets, well, they look like they're exactly the same, and in fact, they are. If I were to line these up, the 0 would match with the 0, the 4 with the 4, the 8 with the 8, the 12 with the 12, so on and so forth. They contain exactly the same elements. So the question then becomes, if I'm given two congruence classes, how do I know when they are equal to one another? Well, this is the perfect lead-in to the next theorem. So we say A is equivalent to C mod n if and only if the congruence class of A is equal to the congruence class of C. So this is an if and only if statement, so it works in either direction. So if I have A is equivalent to C mod n, then this means that the congruence class of A is equal to the congruence class of C. If I have the congruence class of A is equal to the congruence class of C, well, then this also means that A is equivalent to C mod n. And of course, down below, we just have the same thing in coset notation. So take a quick look through that. Again, we're going to be focusing on the notation that I have up here. But let's take a second to actually prove this one, because it's a nice proof. It's not overly that difficult, and it does have this if and only if case, which we haven't done yet. We've always proved in one direction. So we'll start with the more challenging direction, which is going this way in the statement. So what we're doing is we are assuming that we have A is congruent to C mod n. And what we're looking to do is to show that the congruence class of A is equal to the congruence class of C. Now with equality, how do we prove equality of two sets? In order for us to do this, I have to be able to show that every element inside of A is contained in the set C, or the congruence class of C, and vice versa, that everything inside of C is also contained in A. So let's prove this. So let's take an element inside of A and show that it's also inside of C. So we'll let B be any element inside of the congruence class of A. Because remember, this is a set. We can grab any element inside of that set. Well, what does it mean to be inside of that set? Well, it means that B is equivalent to A mod n, when we went and defined what the congruence classes were. So using the assumption that we have, so we're given that A is congruent to C mod n. So if B is congruent to A and A is congruent to C, then the transitive property says that B is congruent to C mod n, which of course means that B is an element inside of the congruence class of C by definition. So I've taken all of the elements inside of here and shown that they're also inside of here. Now I have to do the reverse. I have to take everything inside of C and show that it's also inside of A. It's going to work in exactly the same way, just with a slight twist. So this time, we'll use the variable D. That's inside of the congruence class of C, so any element inside of that set. Again, this means that D is equivalent to C mod n. Now, using the information that we are given, so again, given that A is congruent to C mod n, it's almost in that nice form. I have D to C, A to C. It's not exactly right. But remember, when we're talking about distance away, if I'm going n units to the right or n units to the left, it doesn't matter. It's still a multiple of n units away. So it doesn't need to be exactly in this order. I could say C is equivalent to A mod n, and it's going to mean exactly the same thing. That was based in our original properties of this. So this implies, and I'll do it over here, that C is equivalent to A mod n. Now I have everything in the right order. I have D is equivalent to C, C is equivalent to A, so D is equivalent to A mod n, and by definition now, that implies that D is an element in the congruence class of A. So therefore, with this being true, that everything inside of A is inside of C, everything inside of C is inside of A, that means these two subsets here, or these two sets, are equal, or in this case, congruence classes, mod n. All right, so we've proved one direction. We still need to prove the other direction. Now, luckily enough for us, the other direction is super easy to do. So going in this direction here, what we are assuming this time is that we have the equality of these congruence classes already. And we want to show that A is congruent to C mod n. So how do we do that? Basic properties. Let's take an element A. We know that A is congruent to A mod n. This is true, which, if this is true, means that A is an element inside of the congruence class of A. We are given congruence class of A is equal to the congruence class of C. Thus, A has to also be an element of the congruence class of C, and therefore, by definition, now since A is inside of C, that means A is equivalent to C mod n. And that's the end of our proof. Told you the other way, super easy compared to the first way, but even the first way wasn't all that bad. So now we know when two things are going to be equal to one another. This also means, this gives us an idea of how many unique congruence classes we can possibly have mod n. So this leads us to the next corollary. So two congruence classes module n are either disjoint or they're identical. So we saw that from the proof in itself, that if I have an element inside of one, it has to be an element inside of the other, and vice versa. But one can't have an element in one and not in the other. So it's either the two sets are exactly the same, they contain exactly the same elements, or they have no elements in common. So thus the disjoint, or they are identical. Now in terms of the number of disjoint congruence classes, let's let n be greater than 1. So n is an integer, and consider congruence modulo n. Then one thing we know, again, when we define these congruence classes in terms of the division algorithm, that if a is an integer and n is the remainder, when a is divided by n, then what we have is that the congruence class of A is equal to the congruence class of R. Now, what we know in terms of the total numbers is, again, by this division algorithm, the remainder is bounded below, so R has to be greater than or equal to 0, but it also has to be less than what we're dividing by, strictly less than. So it has to be strictly less than n. So that means we have R could be 0, R could be 1, R could be up to n minus 1, but that's it. As soon as we hit that R is equal to n, we're now repeating, which is exactly what we saw with the example when I did the mod 4 and I did the congruence class of 0 and the congruence class of 4. It was exactly the same sets. So everything before that would have been disjoint sets. So how do we completely partition up the original big set that we are dealing with? Well, again, we look at all of these disjoint sets, and all of them together is ideally what we have. Now this leads us into the next definition, is that if we have all of these sets together, then the set of all congruence classes modulo n is denoted by this z sub n, which we read z mod n. So z mod n is in fact how we partition up z in n disjoint congruence classes. Now we saw an example of this. Again, back to the whiteboard one more time here, folks. So remember from the example when we did n is equal to 2, and we partitioned z up in these two classes. So we had the congruence class of 0. This was equal to the set of all even ints, and 1 was the set of all odd ints. And that makes up the entire set of z. Z is made up of even and odd integers. All the even ones are inside of the congruence class of 0. All the odds are in the congruence class of 1. We are not missing anything. And evens can't interact with odds in that same sort of way. So those classes have to be disjoint from one another. So I look at Z mod 2. This is the congruence class of 0 and the congruence class of 1.